Okay, so we covered basically all of section 5, 11.6, directional derivatives and the gradient vector. And there's one little portion left here that I'm going to talk about. It has to do with tangent planes to level surfaces. So recall that a level surface is, hold on here. Recall that when you take a function of 3 variables and set it equal to a constant, that gives you a level surface. And that surface, just like any surface, if we pick a point on the surface, that point on the surface will have a tangent plane. And we're interested in finding that tangent plane, like you see here in figure 9. So the way you come up with the equation to do that is basically the same kind of approach that we used to show that for a function of 2 variables. Okay, if you look at a level curve for a function of 2 variables in the xy plane, at a point the level curve is perpendicular to its gradient vector. So it's the same kind of setup here. You have a function of 3 variables that set it equal to k. Each variable is a function of t, and then you can take the derivative of both sides with respect to t, and then using the chain rule, and then you end up getting then that the gradient of the function at point of interest is perpendicular to the derivative vector at the time of interest, which will correspond to the point of interest. And of course, that derivative vector is the derivative vector to the space curve that runs through the point P, as you see in figure 9. So remember, the gradient vector is, because it's perpendicular to point P, it's perpendicular to the plane. And so the A, B, and C, if you remember the equation of a plane, you have A times x minus x0, plus B times y minus y0, plus C times z minus z0 equals 0. The A, B, and C can be replaced by the components of the gradient vector. And so what you end up with then is this equation here that gives you the equation of the tangent plane. Okay, and the equation of the tangent plane, naturally, if you have the equation of the tangent plane, there are other things you can find too. Like, for instance, if you wanted to know the normal line to the surface at the point P, the normal line would be the line perpendicular to the plane at the point P. Well, you have, the A, B, and C is represented by those partial derivatives. And so the normal line here, if you wanted the symmetric equations to the normal line to the surface at the point P, those are the symmetric equations of that line. So the partial derivatives of f with respect to x, y, and z replace A, B, and C. And so given these concepts, you can find equations of tangent planes to level surfaces and perpendicular normal lines to level surfaces. And they have a nice example 8 here, which I'm going to let you, look over. It's very straightforward. You're going to be fine. Are there any questions before I stop the recording? Okay, give me a thumbs up if you're good. I always like to end my recording with a few thumbs up anyway. All right, thank you, Samuel. Thank you, Aura, Angela, Yeva. Thank you, Alexander. Wonderful, and a few other people here. I always like to kind of give it, Norina and Arian. Wonderful. All right, I'm going to stop the recording. Thank you, Matthew.